So now that we've given an overview of the structure and functionality of the server components, let's dive into how they're implemented. And we'll take a look at the LockManagerController and the LockManagerService. As you would expect, the LockManagerController isn't the interesting part. It's the service that's the interesting part. And you can get that here at this link in my GitHub repository, which is part of the EX1 project in the WebFlux folder in my Live Lessons GitHub repository. So here we are in the project. You can see that we've got the source, main, Java, server, and that's where we're going to start our discussion. There's also a couple of other helper classes we'll take a look at along the way. So let's first start by taking a look at the LockManager application. And as always, this is the main entry point into the microservice. This looks very similar to what you would have expected from before. We have a main entry point that runs the LockManager application. Where things get a little different from what we've focused on before, however, is that now we're going to configure this microservice to use Java virtual threads to handle the incoming HTTP requests. And this is a super cool example of how you can use beans in Spring to do dependency injection. Just such a great idea. So as you can see here, we have one bean that is the async task executor factory method, and it's going to use a new virtual thread per task executor. So what that means is every time a request comes in, a new virtual thread will be automatically spawned by Spring in order to run the request in a virtual thread. And then down here, we have this very complicated name, protocol handler virtual thread executor customizer, which is also a bean, and it's going to set things up so that deep in the bowels of the underlying web server, it will use virtual threads as well. So we've got virtual threads top to bottom here. That's how you configure them with Spring. Pretty cool technique, and we'll use them in some other code as well. So now let's take a look at the LockManagerController. I'm going to go through this very quickly because it's basically what we looked at before with the walkthrough at the structure functionality level. We auto-wire the LockManagerService. We have a create method. We have an acquire method. And you can see all these things do is they just convert from the HTTP types into Java types, and then they forward them to the service that does the actual work. And this is just a nice separation of concerns so you can focus on things that involve HTTP to native Java transformations in one place, and then delegate or forward to the underlying implementation, which is this LockManagerService. So let's take a look at the LockManagerService. This is way more interesting. So the first thing you can see here is that this has a field called LockManagerMap. And the LockManagerMap is a concurrent hash map, so it can be accessed from multiple threads simultaneously, which is important because, as you just saw, each new HTTP request that comes into this server will run in a separate virtual thread. So we need to make sure we're thread safe and synchronized properly. This is a map that maps something called a LockManager, we'll look at that in a second, to the LockManager's corresponding array blocking queue, which will keep track of the available permits at that point. Let's just take a quick look at LockManager. LockManager is a very simple class that has the name of the LockManager and the number of permits that are allowed in the LockManager. Those are its two fields. We got a couple of accessor methods. We have a constructor, which creates the name, and it puts the permit count as part of the name. And then we've also got some methods to check to see whether or not the two instances of LockManager are the same. And as you can see here, it uses the same technique that we use in our program. And I guess if we were really trying to be super duper paranoid, we would say something like this: objects equal this name, other name. So we don't have to worry about problems that might occur if, for some very strange reason, the name field was null. OK, so that's LockManager. Oh, here's lock, by the way. So LockManager keeps track of locks. And a lock is just another simple type that's going to have the name of the lock, which is just a value, it's just a string. And it has a constructor that sets that field, and it has another accessor method that returns the name. So that's what's going to get passed back and forth, as we'll see here shortly. So going back to the LockManager service, you can see that the LockManager map is a lock manager that is mapped to an array blocking queue of locks. When a client calls the create method, it wants to create a new instance of a semaphore that will have the corresponding permit count that's passed in. And here's what we do. Notice this is returning a mono. So we have to use mono from supplier. That's the factory method that's used to create a new instance of a mono. And inside this, we have a lambda expression. I could have factored this out into a method call, but because it's a little long, but it's not too complicated. So we first start off by making a new array blocking queue of the number of permits that were requested, and we set that to have fair semantics, so things will queue up in round-robin order. We then take that available locks array blocking queue, and we add a bunch of locks to it. Make locks is a clever little factory method that uses reactive programming to generate a range of integers from 0 to count -1. We map each of those things to a string. We then make a new instance of lock with each of the instances having a string from 0 to count -1. We collect those into a list. So we take the stream of fluxes and make them a list, and then we block until the list is fully populated. And we just do that because we want to get back a list of these things. So those are all added to the available locks array blocking queue. We then make a new lock manager, which is going to be given that permit count, and we generate a unique ID. And this is something we get out of the utils class here, which is in the utils folder. And all it does is it generates a random value. It's a 128 byte random value, very large, and we turn it into a string. Then we put the lock manager into the lock manager map and map it to the available locks. And you'll see how this gets used in the rest of the code. And the final thing we do is we print out some debugging information for logging purposes, and we return the lock manager. So that's going to come back to the client as a mono to a lock manager. And we'll see that when we look at the test driver. Let's now take a look at what happens when a client wants to acquire a lock. So the client will have gotten back a lock manager from the create factory method, and then it passes the lock manager in to the acquire method. And then its purpose of this thing is to get a lock, get one lock and one lock only. To do this, we're going to use the mono from callable method because we're returning a mono here. And we're going to go ahead and look up in the lock manager map using the lock manager, try to find the array blocking queue of available locks. If for some strange reason we can't find that available locks return value, then we're going to throw an illegal argument exception because somebody gave us a lock manager that we don't know anything about. Otherwise, we're going to try to be clever. So the first thing we're going to do is we're going to try to pull this array blocking queue. And if we're lucky and there's an item in there and it's available right then and there, we're going to get it. At that point, we didn't have to block, and we're done, and we return the lock. So all is well. However, if all the permits in that semaphore are being used by somebody else at this point, in that case, we're going to have to block. And we can block here because we have a virtual thread that we're running in. So we're going to call the take method on available locks. That will put this thread to sleep until there is, in fact, a lock available in the available locks array blocking queue, at which point take will return, this thread will wake up, we will get the lock, and then we return it. And you can see we will print some diagnostics depending on whether we succeeded or failed here. And this information is used to log stuff on the server side. It doesn't go back to the client, it's done on the server side. And you'll also notice a really funky little technique here. We don't actually need the name of the mono on success because we don't use it. So we just put an underscore there. And that just says this is intentionally not used. That's pretty straightforward. The only thing that's interesting here is the idea that we can either try something non-blocking, and if we're lucky, we get it. Otherwise, we block. Now let's take a look at acquire that's going to get a bunch of permits. Not just one, it wants a bunch of permits. This is much more interesting and much more complicated, especially when we start trying to do this in a non-blocking way using reactive programming techniques. So let's take a look and see how this works. First thing we do is we go get the lock manager. the available locks array blocking queue from the lock manager that's passed in. If, once again, it doesn't find it, we got problems, we throw illegal argument exception, we bail out. If we found the array blocking queue, we're then going to go ahead and create a local list that's going to be used to try to acquire the lock objects in a non-blocking way. So we make an array list that has a number of permits, and this is just a temporary thing that we're going to use for now. And then what we do is we go ahead and we call the mono from supplier method. And this is completely wacky, very fascinating code using the project reactor features, both monos and fluxes. I had a lot of fun writing this code. ChatGPT and I had fun a year ago figuring out how to do this because it's pretty subtle. So here's what we're going to do. We're going to try to acquire the lock, and we'll take a look at try acquire lock in a second. And try acquire lock is passed in the array blocking queue of available locks and the list of locks that we've acquired, which is what's up here. Starts out empty. This from supplier returns a mono, and then we're going to call the repeat operator, and we're going to keep repeating this indefinitely. So try acquire lock is going to keep being called until we end up getting the number of permits that we want. So this is just completely wacky code using reactive programming. This is basically a do-while loop with reactive programming. So we get ourselves a mono, we repeat forever until we have a result that comes back here that equals the number of permits that we want. So once we have that, we're done. And so then we log the results. And then we're going to use a very wacky method on Flux that transforms a flux of integer, which is what we needed here to do the equals, and it does then many, which then, if you recall, then is a suppressing operator. So it's going to suppress the results of flux integer, and instead it will return a flux that contains the list of acquired locks. That was also tremendously fun figuring out how to write that code. So that's what we're doing here. And let's take a look now at try acquire lock. So try acquire lock is actually very similar to the one that we used for the Spring Web MVC version, same basic idea. We come in here, we have the array blocking queue of available locks and a list of locks we're in the process of acquiring up to the count that we need. And the first thing we do is we try to do a non-blocking poll. If we are successful and we obtain a lock, we add that to the acquired locks list, and then we return the number of acquired locks in that list. And recall when we were doing this thing in that repeat take until structure, that we're going to keep going until we get the number of permits that we want. So that's what's going to happen there. So what happens is if we get all the locks when we call try acquire lock, then we're done. However, if we don't get the locks, then what we're going to do is we're going to return all the available locks. If there was nothing here to get when we did a poll, we're going to throw all the available locks that we tried to acquire back into this list. We're going to give it back to the available locks queue. We're going to clear out the list and return a 0, which indicates we got to start all over again from scratch. And the whole reason for doing this is because we're going to have multiple threads trying to come in at the same time and try to acquire the number of permits they need for their acquire call. And because this whole thing is non-blocking and we never want to block, then in that case, we've got to do this clever technique to play games with returning stuff if we can't get what we need. The consequence of this is basically a sort of a wait-free style form of doing semaphore acquisition. And under low contention, it's super fast because it never blocks. Under high contention, it becomes inefficient because it keeps throwing things back after it got them. But it doesn't ever block, which is what we're trying to do. So that's how acquire works. Acquire is a very interesting piece of code. Then the release methods are much simpler, mercifully. We come in, we take a lock manager that we're trying to return a lock to. We go look up the available locks. If we fail, we return Boolean that says we didn't succeed, we return false. If we succeeded, then we go ahead and put the lock back into the available locks. And assuming that people are not futzing around with the protocol incorrectly, this call should work, offers a non-blocking call, it should put it back. But if it doesn't, if for some reason people have not followed the protocol, it'll return false as well. Here is the version of release that takes a list of locks. And what this does, once again, it looks up the lock manager to find the available locks, does some error checking, and then it takes those locks, and for each of the locks that are in the locks list that we are trying to release, which is what is passed here, for each of these things, we turn this into a Java stream, and then we're going to put each of the elements back into the available locks, array blocking queue, and if anything goes wrong, it'll return false, otherwise it'll return true, and we keep track of that, and that's what comes back. This is also a fun example of combining Java streams with the features with reactive types. If I spent some time thinking about this, I probably could write this code to use a flux, but this worked perfectly fine. OK, so that is essentially the server-side implementation. Very subtle, very cool, and as we see when we run the code later, works just fine.